It's a great pleasure to have today an old friend, Sunder Serthuraman, which is now at the University of Arizona. And he will speak about, as you see, condensation, boundary conditions, and effects of a slow site in a zero-range system. Thanks, Sunder, for accepting to give a talk here.
Oh no, it's very nice to be on, it's good to see all of you. So let me talk about something about zero range systems. This is work with Jianfei Xue, who was here at Arizona, but he's now a postdoc at the University of Missouri. And this problem is about how some boundary conditions arise, and since the zero range system can be thought of as sometimes as a queuing system, how maybe a slow queue might develop, something like that. So so let me start here. So of course, we're not going to be dealing with human nature. So so if you're in the so if you're in the grocery store, maybe you'd like to go to the fast queue, but okay, anyway, so this is just a warm up. Okay, anyway, so let me keep going. Okay, so so we're going to try to establish some sort of hydrodynamic limit, and one of the sites in the system, I'll define the system carefully in just a minute, will be slower than the others, in the sense that if you are there, then you may not jump out as quickly as if you're in a different place. And so we want to see how that, understand that phenomenon just a little bit better. And so this is sort of a first exploration of all of that. This work is mostly written down, and it should be on the archive soon. It's not there at the moment. Okay, so let me start with the model, and this is familiar to many of you. So, but for those who may not have seen it, the zero range process is a collection of continuous time random walks, let's say on an integer lattice. So we'll be working with in one dimension, just even on a torus. Okay, so 0 and n will be identified, and so the number of particles or random walks at each location is not, there's no upper bound on that. And the way it moves is that each location has a clock. The clock rings with a certain rate, which depends on the number of particles. So let's say that there's a function g, and so if there's 3 particles here, this site will ring at rate g of 3. Then at random, one of these particles is chosen, and we're going to be considering the symmetric system. So that chosen particle will either move to the nearest left or the nearest right with equal probability. So that's and we're going to make one of these slides a little bit different. We'll put a defect into the system. So site 0 will have a jump rate which is slowed down by this factor n to the minus beta, and n, as you see here, will take the role of a scaling parameter, and so so if you're at this location 0, then your jumping rates are much slower than if you're not there. So particles are going to move around. If they get to 0, they may accumulate, and so you can call that aggregation or condensation, although condensation means different things in different contexts. Okay, so that's the model, and we should say what the g is, this function. So at the in the previous slide it was sort of arbitrary, but let's now take g to be a function of the particle number x as particle number to another power alpha. Okay, and we'll take alpha to be between 0 and 1. Okay, so just for those who haven't seen the system before, when alpha is equal to 1, this system can be thought of as actually independent particles, so there would be no interaction effect. So that's something that can be understood. If G of 3 is equal to 3, you can think of each particle as carrying its own exponential 1 clock and not interacting with the others. Okay, so we're allowing alpha to go from 0 to 1. Alpha equals to 0, that would be maybe a bounded rate case, and we'll have something to say about that at the end. Okay, so at the moment, we'll take alpha strictly positive. Okay, so formally, the generator of the process can be written down in this way. So just as a way to introduce notation. So let's say C is the system of particle numbers. C of K is the number of particles at site K. And so what this means is that a particle at location K moved over to K plus 1, and this is the updated configuration. That has this rate, and remember, we're symmetrically moving once you have chosen to jump. And so G sub K is just the rate that we mentioned before, and then at 0, it's the slowdown. Okay, and this is, we're going to be later speeding up by n squared since we are imposing symmetric movements. Okay, so that'll be later on. Okay, so this sort of problem is not new, and there's a very nice paper by Tertu and Patricia and Gunther on such a problem in exclusion systems. So I just mentioned it in context. So if your slow side is 0, then you maybe make the jumping rate from there as something similar to what we were imposing. We were looking at their paper actually. So then they were able to derive, if beta is large, they were able to derive a hydrodynamic limit for the mass in the system with this kind of Neumann condition. So, and they also mentioned that when beta is equal to 1 or beta less than 1, then different behaviors should occur. And so they mentioned a Robin type boundary condition when beta is equal to 1. Okay, and if beta is less than 1, then somehow the slow side is not that defective, and you don't really see it in hydrodynamics. Okay, so that's one paper, and we were also very much interested in this paper of Milton, Claudio, and Augusto, which considered, in some sense, the zero range also in a trap environment. You can think of many defects, and they were considering independent particles. And so if you have just to mention it again in context, so if you have let's say a finite measure on the torus, on the continuum torus, then, and you now put, affect the, multiply the jump rate G by this kind of factor for each site K. Okay, so so if W is absolutely continuous with respect to the Lebesgue measure, this will be order 1, but it could have some point masses, for instance. So for instance, if you have a point mass at 0, that's the case that we're sort of interested in, then so you're basically slowing down at 0 by the beta there would be, in terms of our notation, would be 1, so n to the minus 1, and then they were able to, they have a much different result, and it's a little bit more general result for independent particles, but in this context, this is the hydrodynamic limit that they solved. And so you see that the zero location picks up actually in the hydrodynamic scale, it picks up a point mass, an evolving point mass. And that point, the level of the point mass, if there's only one, you can rewrite in terms of some mass conservation relation. So in some sense, we're looking at zero range where alpha may be less than one, and so there will be interacting particles, and so and the particle number is unbounded, and so the relation also between beta and alpha is we were kind of curious what that might be, and as you might suspect from the previous results, three different things happen if beta is bigger than alpha, beta equals to alpha, and beta less than alpha, and so this is the point of view that we have. Feel free to jump in and ask any questions or clarifications. Okay, so let's try to set up the notation and the ingredients. Okay, so one of them will be the invariant measure for the system. So zero range process is of course something that allows for explicit invariant measures, and so these are these products of Poisson-like distributions. If G of n is equal to n, this is exactly Poisson, right? For those who haven't seen this before. And so let's define this one-dimensional marginal, and the parameter phi here is so this family is determined by phi, and phi varies, and so let's choose phi so that the mean of this measure is actually rho. So we'll call that phi as capital Phi of rho. So this is the fugacity, so-called fugacity of the system, and one can actually calculate the fugacity in terms of an expected value of the rate. Actually, that's an explicit calculation that one could do. Okay. Anyway, so this is this is one of the ingredients, and so we put these together. So at the non-slow sites, let's put product over these measures, and at the slow site, as you can imagine, it's slow, right? So we expect more particles there. So somehow the density, or in this case, the fugacity will be a little bit larger. So it turns out that this is the form of the fugacity that you should put at the slow site in order for this measure to be invariant. And the number C here would be some sort of equilibrium density. Okay, so these are these measures, and so.
Sunder, I have a question from Ricardo.
Yeah.
He asked, is beta here just a parameter, or is it related to the temperature?
No, there's this is just it's just an arbitrary parameter. We just chose beta because somehow we chose alpha for the other one. So it has nothing to do with the temperature, just a parameter. Okay, thanks for that question. Okay, so great. So we're going to so before we get to the hydrodynamic limit, let's discuss the behavior under the invariant measure. So we expect some accumulation at the slow site. How high is that in terms of n? That's one of the questions. Let's just figure that out. These are somewhat routine calculations, but let me just go through them. So let's form the empirical measure, okay, and this is the one off the excluding the slow site. Okay, so I mean this is a trivial thing. So if you're away from the origin, of course, these variables are into IID, and so the empirical measure is basically is converging to this constant. Okay, and but at the slow side, okay, that's the thing that we want to assess. And so the expected number of particles starting from one of these invariant measures is of order n to the power beta divided by alpha. Okay, so okay, great. Okay, so this Rn has in it, the information of alpha and beta, and so that's expressed, although it's not explicit here, it's in the Rnc. Okay, so this is the level of particles at the slow site in equilibrium, and so you can conclude that if we're going to be looking at the hydrodynamic limit, so we're going to be scaling particle numbers by n, and we're going to be speeding up by n squared in time. So the space scaling, grid scaling will be 1 over n, but the time scaling will be n squared. So in the grid scaling n to the -1, that's the hydrodynamic scaling. So if beta is less than alpha, then of course you don't really feel the slow side. That's maybe intuitive. If beta is small enough, then the defect is not seen. If beta is equal to alpha, then you see from the previous result that the level of particles is order n, and in this case, beta is equal to alpha, and so you get some constant here. And if beta is bigger than alpha, then with respect to the invariant measure, then you're also getting this constant, but the scaling is not n to the -1. It's a little bit, you have to divide by a little bit larger power of n. Okay, so particles are really aggregating in that case. So it's very slow. Okay, anyway, so putting that together with respect to this empirical measure, we see that if beta is less than alpha, then you don't feel the slow side, and so you're just going to this constant. This is all with respect to the invariant measure. And if beta is equal to alpha, you're picking up a point mass. And if beta is bigger than alpha, then and you restrict your test function to the open interval 0, macroscopic open interval 0 to 1, then you're also picking up just a constant. So we're avoiding the slow side in this last result. Okay, so let's come to the dynamical or hydrodynamic limit. Okay, so we're going to speed up time here by n squared. And so let's just change the variable eta t to eta t. And so the empirical measure now, with this super n will be with respect to the speeded up process. Okay, and it diffuses in this scale, this diffusive scale. And so we're going to consider subcritical and supercritical cases as well. Okay, so what's the initial distribution? So let's pick something which is in some sense perturbative of the invariant measure. It has relative entropy bounded like this. So every location you can modify a little bit, and this is a technical condition. So we'll assume that mu n can be stochastically bounded by one of these invariant measures for some density C prime. And since we chose the g to be g of x to be x to the power alpha, it's an increasing function in x. And so there's some technical tools that you can use for such zero-range processes where the rate is an increasing function. It's this is for those who haven't seen it before. It's attractiveness, and so there's some basic couplings and things like this that you can use. And so this last condition is a technical one, but it allows for some of the proofs. Okay, so what would be an example of one of these measures that we could start from, just to keep something in mind? You can build local equilibrium measures. So these will be a product of the marginals that we had before, but the fugacities would depend on the location. And so if you just pick a continuous function on the torus, if beta is less than alpha, you could just take it to be sampled the continuous function at points k over n, and put in the appropriate fugacity there, and then form that measure. That mu n would satisfy the previous conditions. So when beta is equal to alpha, you could do the same thing, except at k equals to 0, we want to build up a little bit more. So you put the fugacity as order n to the alpha. So beta is equal to alpha in this case. So then if you go through the static hydrodynamic limit, we'll pick up this measure of the torus. And if beta is bigger than alpha, again, let's work on the open interval 0 to 1, and set the fugacity at the slow side to be n to the beta times the spectrum. Okay, so this should have been 0, n. Sorry, that's not k, 0, 0, n. Sorry, that's a typo. Okay, so there's lots of measures which satisfy those conditions. Okay, these are some natural ones. Okay, so let's start with one of these initial distributions mu n, and let's say associated with rho naught. Okay, so let's just go through relatively quickly the subcritical case. That's the one where we expect not to really see the defect. So let's take a mu n associated with rho naught, and so we're trying to prove this kind of thing, which is the usual hydrodynamic formulation, one of the usual formulations, and so this rho would satisfy this nonlinear heat equation. Okay, so phi is the fugacity with respect to the rate g of k equals to k to the power alpha. Okay, so this is the result that we expect in the so-called subcritical case, and I guess the so-called GPV method is well known to pretty much all of us, but let me just, as a comfort, go through it, if you don't mind. Okay, so let's consider the Martingale that one can form. So we're trying to assess this quantity, which is if G is something like an indicator function, this would be just the average number of particles in the support of that indicator function. So we're looking at the evolution of this over time. So let's form this Martingale that we're allowed to do, and the expected value of the square is it's a well-known computation. One can see that it's 1 over n, and this quantity right here explicitly one can compute in the zero-range process, and delta n is discretization of the continuum Laplacian, the usual discretization. Okay, so one has this kind of thing, and once you have this kind of statement for the square, then one easily gets this convergence and probability, and so then the goal is to, the GPV goal is to replace the nonlinear functions in the correct way, and so we could replace delta n with delta, and gk, if k is not equal to 0, gk is just equal to g, and so we can replace that by a function of the local particle number. So this is the notation for the average number of particles in a small macroscopic block of width the order beta. That's what this is. And so one can do this. The effect of the slow side is not here because of those previous static computations. So here we'll have a k could be 0 here, k could be 0, in the evaluation of this quantity, and so both of them are going to 0. Sorry,
you use here coupling, right, to avoid large values.
That's right.
Eta.
Yeah. So here coupling is exactly. So this is one place where we use coupling. So here this first inequality is using the coupling, and that mu n is assumed to be less than this one here. So this inequality is using the basic coupling and the assumption that mu n is less than Rn. So this is and G0 is an increasing function of eta, and so this inequality is allowed. And G0 is n to the minus beta, so I just pull out the n to the minus beta here, and then I have just this one. And this is an explicit computation. We saw that this is actually just n to the beta times something, and so you just get this. So this one goes away, and then this one, we also explicitly computed this one as n to the beta divided by alpha, and beta is less than 1, so this combination is going to 0 as n goes to 0. So both inequality, the first inequalities in both statements are definitely using attractiveness. Okay, so that's a general point in this kind of thing. The local stuff, in order to make truncation bounds, either you don't do the truncation or you. That's a more of an abstract general question, I think, in this kind of hydrodynamic problems. So we're using attractiveness here to give us some control. Okay, so tightness. So we can prove things are tight, and then so we can close up the system and arrive with respect to a limit point that these limit points right here would satisfy this type of weak equation, and then with a uniqueness criterion, one can push through and then get the statement that we wanted. Okay, so in the case beta less than alpha, these calculations show that the slow side doesn't really matter in this kind of hydrodynamic scaling. Okay, so that's the subcritical case. Let's go to the critical and supercritical cases. Okay, so is everybody okay with this? So okay, so let's try these cases. Okay, so the expected number of particles, let's say, is n to the power. So this is something we calculated before in the so-called static computation. It's n to the power beta divided by alpha. So things are growing. Okay, so it's either growing at order n if beta is equal to alpha, or superlinearly in n. Okay, so let's take a test function which is compactly supported in the macroscopic open interval 0 to 1. So we're avoiding the slow side here. Okay, and the same argument that we gave before will give us this kind of statement. And moreover, we can go to the limit points, and so we'll get a weak formulation for a class of test functions. Okay, but we haven't said, and we know that the boundaries matter. There is a significant accumulation at the slow side, and so we need to. At this point, we have something in the bulk, but we need to figure out what's going on at the boundary. Okay, so that's the difference from the subcritical case. So we should consider the boundary behavior. So let me just start from there's a way to get to 0 from the plus side or from the minus side, whichever way you're looking at. Let's just do one of the ways. Okay, and this is the statement that we would like to show. We would like to show that, so G0, remember this is this funny notation that we have. G0 is the slowed down rate. So G0 has an n to the minus beta times G. That's what this is. And we're going to say that this function of the particle number at the slow site is close to the fugacity of the local density just next to it. Okay, that's the main thing. Let me try to argue why that is reasonable to expect. Okay, so so this is something that we also saw that the paper Milton, Claudio, and Augusto, they were also looking at this kind of replacements or this kind of in a different context, but we were inspired by that. And so so if you look at the we're starting from mu n. Mu n is not so far from the invariant measure, and so in the invariant measure, the rates in and rates out match. So this rate is the rate out of 0. It should match something like the rate out of 1. So so that's the intuition that, so we want to get out of the slow site, which is trouble for us, to something like site 1, which is next door, which is has access to more regular behavior. And so this is a first step. And so we would like to establish that. And if we can establish that, then from 1, one can access the local density to the right of 1, this quantity here. And then from here, one tries to get to a macroscopic average. Okay, so this is the scheme. Okay, so is that okay? Any questions about that? So that's the scheme. Okay, so if we can do that scheme, then we would so this statement informally, let me just write it as this, that the rate G0, the rate out of 0 is close to this function of the particle local macroscopic average. And since this one should be just the average of the what we're trying to derive, the hydrodynamic density, this one should be close to whatever this thing is. So then conclude that the rate out should be close to fugacity at the density at time. If you're looking at time s here, the density at time s at the location 0, or as you come into 0. So that's the so this is a key thing which will work for both critical and subcritical, supercritical cases. Okay, so if you now let's just consider the beta equals to alpha case. So let's try to figure out what this means in this setting. So so g of x is x to the alpha, right? Let me just remind you of that. And and G0 is n to the minus beta g of x, which is when beta is equal to alpha, you can just put in the n inside this parentheses, all to the power alpha. So phi of rho of s at 0 is close to this. That's what we were argued in the previous slide. This one from here is exactly equal to this, and this one right here is the scaled particle number at the slow site, but we have mass conservation in the system. Okay, so there's the dynamic 0-inch dynamics. There's no birth or death. So so this should be the full particle number, total particle number on the torus at time s minus the stuff away from the slow site. Okay, so this so you have this kind of relation, and so this full total number is actually not changing. It's just the full total number at time 0 from S to 0, right? And then this one is exactly this. As that's how we chose the mu n, let's say, and let's say the mu n is associated to this kind of rho naught plus m naught times delta at 0. Let's say that mu n is associated to that initial profile. Then, and also away from the slow sites, we should get the density on the open interval. Okay, so I just write that like this, and finally, this quantity here that we had in the previous slide, this one right here, should be the size of the atom at 0. So at time s. So that the size of the atom will be determined by the hydrodynamic solution on the bulk. That's what we're getting when beta is equal to alpha. So that's how the boundary condition is for the and that matches what Milton, Claudio, and Augusto did for the independent case. Okay, updating it to alpha. Okay, so let me go to the supercritical case, and so in this, we're choosing diffusive timescale. So the intuition is that things are really large on the slow side. Things are not changing much in that timescale. So the number of particles at time s at the slow site is not, we would like to argue it's not that different from the initial value. Okay, and one can formally write this down, right? This is just concentration of particles again. So you can make these kind of bounds right here, and so we're off the slow site, and so this one by typical entropy inequality, one can see that this is of order n. This is also of order n. Okay, but if we divide this now by n to the power minus beta divided by alpha, remember beta is bigger than alpha, so this is bigger than, so this is n to a power bigger than, 1 over n to a power bigger than 1, so this thing is going to go to 0. So with respect to this scaling factor, this difference is small. And so keeping that in mind, so starting from, we're starting from this mu n. So G0, the rate out, the particle number here is exactly equal to this, right? This is using this kind of this business here. And so we can replace this e to s by e to 0 just by the previous calculation, because we're multiplying by n to the minus beta divided by alpha. And this one right here, we did in the static computation. So this one is going to a constant. Okay, so this constant C was the C is the density that mu n has relative entropy order n with respect to the invariant measure, where the invariant density was C. So that's what the C is, and so we get this boundary condition in the supercritical case, beta bigger than alpha. So this is this equality. This is this thing that we had in blue before, and so this one right here we're saying is basically phi of C. So we're able to get a Dirichlet condition. So rho at, so just invert the phi's. So rho at time s at nearby 0 should be close to C. So that's the boundary condition we get in the supercritical case. Is that okay for everybody? Any questions?
Oh, that's fine.
Great. So, natural question is, what if you had more than one defect, right? In fact, in the paper by Milton, Claudio, and Augusto, they did many defects, in fact. So we're not able to do their setting exactly, but we have some, a case of their setting. So suppose that you have some sites, macroscopic sites xi, which are distinct, so they're separated. Okay, so you have a finite number of them. Let's say you have L of them. So here's your torus in orange. Okay, and these are the L points, and each one is a defect in some way. And so let's say that we're going to slow down the usual rate by this kind of factor. Each site will be slowed down by, n to the minus beta sub I, but then let me just add on 1 over lambda I. We could have done that in the one slow site, but we would have just been able to scale out the lambda. So we didn't put it there when we discussed it, but we can put in the lambdas here if we wanted. Okay, and so let's say that the slow sites are K1, N, KLN, and these scale after you divide by N to X1 through XL. And let's say that the numbers, so XJ would be one of these critical locations when beta J is equal to alpha, and it's a supercritical one when the beta J is bigger than alpha. Okay, so the same proof actually will work here. So just a more complicated statement. So if at a point, so you can imagine the torus is, you can just separate it into intervals, and there should be a boundary condition on each of the subintervals. So that's basically what's going on. So when beta I is less than alpha, then you don't feel the slow site. Beta I is equal to alpha, point mass is picked up. Okay, and beta is bigger than alpha, then you get this Dirichlet condition. So we're still starting from UN, which is has order and relative entropy with respect to one of these invariant measures. Okay, so the invariant measure will be updated, right? Because we have to its product with the usual marginal at the non-slow sites, and at the slow sites we should take this kind of fugacity. Okay, so if you take mu n with relative entropy order n with respect to one of these now, then let's say it also initially is associated with this kind of profile. Okay, so in the bulk you have rho naught, and then at the slow sites, if at the critical slow sites you have maybe some initial atoms, then one gets the statement that I was just saying informally about, you look at subintervals, and so if you form pi t as this kind of object, then the hydrodynamic profile will be in this form, and in the bulk it's satisfying this heat equation as before, and at the critical locations the atom is evolving according to this formula, which is what we saw before. Okay, and at the supercritical ones, you have this Dirichlet condition, so I just point out that here we use mass conservation to actually get a formula here, but one has this formula already right here. So we're mass conservation is not, one can't rewrite the MJs completely in terms of like a simple formula of mass conservation when you have more. So this is the result. So okay, so let me see, how am I doing on time? So let's so maybe I'm getting near the end. So let me just mention some other complements that might be of interest. So So we started from a measure mu n, which is has relative order n relative entropy with respect to one of these Rn's, and the Rn's are formed like this. Okay, but here you see that even at these points where beta is bigger than alpha, the C is the same. So the level of condensation, and so the Dirichlet condition is the same. So suppose that you wanted the Dirichlet condition to be C1 at one site and C2 at the other site. So then, suppose that we wanted something like this at the, if we wanted this kind of Dirichlet condition. So how do we, so again, you have two, let's say you have two locations and the beta 1, beta 2, and so forth. Okay, and so we'll multiply the usual rate by something like this, and each of the betas is bigger than alpha. So it's the supercritical, let's say two supercritical slow sites. And if you just now look at the product measure where you change the marginal to be the this fugacity, then that's not invariant anymore to the dynamics. So that's unfortunate. So we would like to take something which is order n relative entropy with respect to this product measure, where you put this fugacity at the two slow sites and the usual one at the other sites. But that measure is not invariant to the zero range dynamics. Okay, but but however, we would expect this kind of result. So how to derive that? I just mentioned just briefly how we can do it. So we just perturb the zero range dynamics by a Glauber term, where we have some, so at one of the sites, we're putting more particles, and that's what this means. This means that we put a particle is born at K1 with this rate. We put some rates, and then we also make it so that at the other side you may go down by 1. Okay, and so one can choose the Glauber rates so that when we multiply by n squared, that this will be order n. So these gamma n plus gamma n minus will be like 1 over n effectively. And one can choose, the form of gamma plus gamma minus, so that with respect to this perturbed generator, the product measure that we want it to be invariant will be invariant. Okay, so so just as a sketch, so under the perturbed dynamics, we should get the hydrodynamic evolution that we wanted. And the number of particles, born or annihilated, it will be order n. That's because of this condition. And we can bring in some comparisons. Initially with large probability, we can, so eta plus minus epsilon, this corresponds to the perturbed level of where the condensation level density is increased by epsilon or decreased by epsilon. So there will be more particles if you increase Ci plus epsilon. Initially, there will be more particles in this R tilde n. So one can get this. So eta 0 is just starting from the usual Rn that we mentioned. And so this one just is adding just a little bit more density at one of the sites. And so one can get this kind of thing. And so if we can, through some coupling, we can also make sure that this inequality holds, because only this many particles are generated, and so you don't really destroy this relation with large probability. And then by some squeezing, one can get the hydrodynamic limit for eta from the hydrodynamic limit for these, which we know how to do. That's step 1. So that's the scheme that we're thinking here. And another one would be, well, let me maybe skip. If I can come back to this if there's a question. So we can also here we're always okay, maybe so we're always looking at something order n with respect to one of these invariant measures which respects the slow side and puts lots of particles at the slow side in order to make it invariant, right? So suppose that you wanted to start from a flat invariant measure, something where is perturbative of mu n, where mu n is just product of the marginals even at the slow side. Okay, and if we start with something which so if beta is less than alpha, this is actually order n, and so the previous results will hold. Okay, and so but if beta is bigger than alpha, that's the maybe sort of interesting case. Then this flat measure with respect to the invariant measure for the dynamics with let's say one slow side is going to be n to the beta, divided by alpha. So it's superlinear in n. But we expect what's going on in the bulk. You still satisfy the heat equation, but now you should have Dirichlet boundary conditions like this. So the mass is, as here in the macroscopic time t, as t goes to infinity, all the mass will get sucked into the macroscopic site zero. So this is what we expect, and we can do this for independent particles. Okay, so and it's still open for us how to do it for interacting particles. So for independent particles, there's some coupling that we can do. So that works out. Let me just mention very briefly what happened, the bounded case. So if alpha is equal to 0, then if you look at that formula that we had for G, then it reduces to this, the indicator, this kind of rate. And if we make a site slow, then we can do so by just simply multiplying by a factor factor smaller than 1 over lambda, where lambda is bigger than 1. Okay, so this is kind of interesting. So the fugacity for the invariant measures at the slow side will be in this form, and at the non-slow sides will be like this. And so at the slow side, this fugacity lambda phi of C has to be, in this case, less than 1, the max of G. So the invariant densities which are allowed are less than this value, and so this is like the max density allowed. So in the bulk, one should still, even in the bounded case, one should still get this equation. Okay, and but at the slow side, so this is this is the rate at 0. I just wrote it out explicitly here. This should be close to this thing here, which is what we had, in blue in a previous slide. And so this is less than this. So I guess this T should be an S, sorry. So rho S, so at macroscopically, the density, however, even though it satisfies this equation, at the defect, macroscopic defect, it should be less than the max density allowed. So we expect that what one should get is this equation with this restriction, and with the restriction that it's less than or equal to 1. Not 1. This 1 should be this value. Sorry, that's a typo. So this 1, where we see 1, I mean this value here. Okay, so when rho is less than or equal, rho should be less, always at the macroscopic defect, it should be less than or equal to this max density. If it's strictly less, then the flow into the slow side is not much, and it actually it doesn't matter. But if the density actually equals this max density value, then some of the density is leaked into the defect, and there's a storage, and so an atom forms. So that atom is non-negative in that case, and the atom is strictly equal to 0 in this case. So and if you're only one slow side, then you can also solve for M of S in terms of mass conservation. And so one can write down a system for the joint evolution here. And so this last part is we haven't written down this last part, but this is what we expect. And anyway, the proofs, the inhomogeneity is the main problem, and so we use attractiveness. One dimension is also useful. There's some spectral gap bounds which come into play sometimes, and the weak uniqueness of the weak solutions is also maybe of interest to some PD people. And anyway, so I guess there's a lot of questions that we can ask. I just put down some questions here. So why don't I finish here? Thank you for your attention.
Well, thank you very much, Sunder, for this very nice talk. We're now open for questions. So maybe I'll start with one before people entering. But did I understand correctly that you could try to investigate how these, so if you have more than one slow slide, how the densities, so if you rescale time further than diffusively, what you'll see and are these masses changing over these slow sides. Could you consider that, and could you guess what is the evolution of these mass in these among these slow sides?
Yeah, no, that's a wonderful question. We didn't clearly we didn't address that here. It is something to address, I think, and that one I'm not sure. I'm not sure how to do that one.
Mm-hmm. And well, and a technical question. In this case, G equal to 1, do you still need attractiveness? Because usually you need it to bound high densities, but here with G bounded by 1, do you still need it, or?
It's useful.
Okay.
It's useful. So yeah, that G equals to 1 could be changed to a bounded increasing function.
But you still need attractiveness. So you still need G.
We needed it various places. There's the local 1 block and 2 block. We can we haven't written down completely that part. But attractiveness certainly can be used. There's a thought one could use something else there. But we have to look into it.
Good. So I have questions here from Milton. So Milton, maybe you unmute yourself and you ask your question. Milton. Okay, so he's saying it's too noisy there, so I'll just read. So he's asking about if you need a spectral gap estimate. And then there is a second question saying that, well, at the end, all the mass will be concentrated on one side in these in the first model. So, but is that true also in the hydrodynamical limit? If I understood correctly your question, Milton. So first one is, do you need a spectral gap estimate in these derivation?
There is, we use it. It's maybe not completely needed, but it's convenient. So let me make this bigger. So so this one right here, Yeah, this one right here doesn't use one. This is, the usual trick where we, we get to we try to bound this function times a test function, and we put things onto the test function, and then we use the usual. Maybe that's a non-gradient idea. You take the square root of the difference times the square root of the sum and things like that, and then do some Cauchy-Schwarz. So this one doesn't use it. These two are using it, one might be able to avoid, but we do use it here in these two. And about the build up on the slow side, I guess there is I guess in the critical case, is that what you're asking? Anyway, nice to interact with you, Milton. So the one has a buildup of the atom, right? In the critical case, that's certainly there macroscopically. Where's that? Yeah. So macroscopically, this is building up in the critical case. And Claudio's question about how to maybe find an atom, but in a different scaling, is a relevant one, and we haven't started in on that one yet. And we haven't gone there yet. We still have to, most of this is written down carefully. Just have to organize it a little bit to put it onto the archive, hopefully very soon.
Yeah, because a natural question would be to start with n to some power particles. So what you guess that these uniformly distributed among these torus, and what you expect is that these slow sides will absorb this mass, and how so this mass will be distributed among these slow sides in diffusive scaling. So
no, that's this is I know that. Of course, we've discussed other equations, condensation, things like this, and these are all extremely good questions.
So, yeah, just to mention to you so that maybe you can think about it. So, any other question? So, if there are no other questions, well, let's thank Sunder again for this very nice talk. Thank you, Sunder. And then remind that next Wednesday we'll have Marcelo Hilario, which is giving a talk at this time. So have a nice week and see you next Wednesday. Bye-bye. Thanks.